Ladies and gentlemen, good afternoon. My name is Alex Mugnai. I'm working for the company TAS, and I'll have the pleasure of leading the active and passive safety session this afternoon. It's the last one, so I'm sure it's going to be super interesting, especially before the ceremony award. So we will start now with the first presentation from Mr. Libner from BMW, which will be presenting a paper on driver intent interference at urban intersection using the intelligence driver model. Thank you.
Well, thank you. Today I present some results that have been obtained within the research initiative COFAS that is funded by the German government. I'm going to talk about driver intent inference and about velocity-based right turn prediction in particular. So I'm going to focus on the scenario shown in the upper left, where we have an orange vehicle that might or might not be turning right, and we'd like to warn the driver of a cyclist that is moving parallel to the street if and only if the driver actually intends to do a right turn. So our mission is first to detect, or rather predict, right turn maneuvers, and second to issue a warning around 2 seconds before the car reaches a pedestrian crossing, so as to allow the driver enough time to react. Now, there have been a couple of works focusing on this issue in the past years. However, the important point is that, in contrast, we would like to include situations with preceding vehicles into our considerations. So if you have a preceding vehicle, then the velocity profile of this preceding vehicle will influence our own and thereby makes the task of velocity-based driver intent prediction much more challenging. Now, you might wonder, why do we care about the velocity profile in the first place? Why not just use the indicator? Well, as a study of the Auto Club Europa in 2008 has shown, in Germany at least, only in 80% of all cases the indicator is set for turning maneuvers. Also, the indicator might be set although the driver is actually intending to go straight. So the velocity profile could be used to detect this discrepancy. And last but not least, the indicator signal might just not be available, which is the case if we want to reason about other vehicles that we can only observe from the outside. Also, you might wonder why we chose to use a model-based approach rather than a support vector machine or a neural network. So in fact, we're using both of them in other applications, and that's certainly very powerful machine learning tools. However, they also have their weaknesses, which is their lack of transparency, and that the results we obtain cannot be used to make predictions about the future as easily as we can using an explicit model. Also, I talked about including a preceding vehicle into our considerations. So if we have all the possible trajectories of a preceding vehicle and all possible trajectories of our own, then we've got a very big space of possible inputs to our system. So we would need a lot of training data for a non-heuristic model to generalize well to arbitrary situations. Talking of training data, this is the intersection we used for our experiments, crossing it like 165 times doing a right turn maneuver and 80 times going straight. We used the GPS traces that we obtained from a high precision carrier phase GPS-INS platform to build a map consisting of circular arc splines. So circular arc splines do have a lot of advantages above other representations, which is that mapping of arbitrary points can be done computationally very efficient, that they have a very compact representation, so there are only very few parameters needed to model each individual arc. And finally, that the curvature is directly represented in the map. Looking at the diagram, you can see the start of the map, you can see the stop line that is the stop line of the traffic light, and you can see the pedestrian crossing that we're talking about. Now, we use this map to transform our two-dimensional trajectories into one-dimensional velocity profiles, so as to reduce the complexity that we are dealing with. Looking at those velocity profiles, we can see first 2 major stopping points, which is at around 13 meters, which corresponds to the stop line of the traffic light, and around 44 meters, which corresponds to the pedestrian crossing. We can also see notable differences between the two velocity profiles for turning right and going straight from around 20 to 30 meters onwards, depending on whether the driver had to stop at the traffic light or not. Now, with this knowledge, we would like to create a model that allows us to simulate typical driver behavior for both cases of going straight and turning right, and then compare this to the behavior that we actually observe of our own driver to infer the most likely driver intent. In this context, we are using the intelligent driver model that has first been published by Mr. Treiber, Hennecke, and Helbig in 2000. And it basically models driver behavior of two terms. One that is characterized by a maximum acceleration parameter A, the actual velocity V, and a desired velocity U, which corresponds to the free driving behavior. And the second term, which models the car following behavior, characterized by a desired gap D star and the actual gap D with respect to the preceding vehicle. Now, in a typical instantiation of the model, the desired velocity U will be a constant. For our purposes, however, we need the desired velocity U to model the turn-related deceleration of the driver before doing a right turn. So what we do is basically we take the first term of the equation and we rewrite it so as to obtain a desired velocity profile that is dependent on our distance variable s. Now, using a single sample trajectory that characterizes typical driver behavior, like the one here, we can obtain the desired velocity profile for this trajectory. So, as you will notice, we need the parameter A, which can be estimated based on the acceleration phase after completing the turn. So now you might wonder, what do we need the desired velocity profile for? As it turns out, desired velocity profiles generalize very well to arbitrary situations. So let's say we take a virtual zero velocity obstacle and place it at the stop line of the traffic light. And then we start a simulation using the IDM equation starting with 8 meters per second. And what we get is a red trajectory here. And then, once we reach the velocity zero, we remove the obstacle, and what we get is the second part of the red trajectory. And now if you compare this with trajectories that we actually observed of vehicles stopping at the traffic light, then it matches very, very well, although the desired velocity profile that we used for this simulation has actually been obtained from a completely different trajectory. Now, of course, we didn't just use one single intersection crossing to obtain our driver model. Instead, we used 50 right turn maneuvers. For each of them, we calculated the desired velocity profile and the corresponding parameter A, and we clustered them using k-means into 3 different driver behaviors, each with their own distribution of the parameter A. And as you will see as well, is that we used 4 different driver intents actually. So we used the one for going straight, we used one for stopping at the stop line of the traffic light, one for turning right, and one for turning right but stopping before crossing the intersection, the pedestrian crossing. So altogether we got 24 hypotheses, each corresponding to one of those intents and a set of parameters. So basically, having those intentions and the hypothesis, the problem of driver intent inference actually boils down to calculating probabilities for each of those hypotheses, given a not yet defined observation O. And the reason why I didn't define this observation yet is actually that there are a lot of different possibilities how to define it. So in this paper, we investigated 2 of them. And for the first one, we'd like to rewrite the probability for a hypothesis given the observation as product of the prior probability for this hypothesis, which can be obtained from the statistics of the previous slide, and some term which is basically just the likelihood of our measurement given the hypothesis. So what we can do now is we use a simulation-based approach that is starting from some point of time, let's say when we reach a distance of 30 meters, we go back in time for 1 second, consider the velocity values and the distance values we got at this point, and then start a simulation from 1 second in the past up to the current point of time for each of the hypotheses, which you see here. And then we take the final values and calculate the probability of our observation based basically on the distance between the final value and our actual driver behavior, which can also be seen as a bivariate Gaussian distribution. For the case of simply turning right without a preceding vehicle, this is very easy. So we actually, in both cases, both at 30 meters and 40 meters, we will get a very clear result saying this driver is most likely going to do a right turn, or that he's going to do a right turn, but he's going to stop in front of the pedestrian crossing. Now, it's much more complicated when you look at the case of a preceding vehicle. The black line indicates the gap between our own and the preceding vehicle. And as you can see, we're approaching the stop line of the traffic light. We both have to wait in front of the traffic light, and then we accelerate. I'm following my preceding vehicle, and finally, the preceding vehicle is turning right, and we can accelerate so as to go straight. Now, what you can see in the simulation runs is that for a distance of 28 meters, all the hypotheses, or the simulation results for all the hypotheses actually looks the same, which is because our own driver's behavior is dominated by that of the preceding vehicle. So it's actually not possible to say anything about his intents, which is reflected in the probabilities we see above. On the other hand, if you look at the simulation run for 36 meters, then the preceding vehicle has turned. We have no preceding vehicle anymore. The driver is accelerating, and the only hypotheses that fit this behavior now are the hypotheses that correspond to the intent of going straight, which is reflected in the simulation results. Again, we have a very high probability for going straight. So to put all this together, as you can see, this approach is able to express ignorance in situations where it's just not possible to say anything about the driver's intent, but still it's possible to say something at a certain point of time, so to a certain extent. The drawback of this method is that at each point of time, at each point when we want to do inference, we have to consider a whole simulation run. So we have to do the simulation run for each time step, which is not as bad because actually it's still real-time capable, but we can do better than that. And this is the so-called comparison-based approach. The comparison-based approach simply compares the values that we observe, the acceleration values that we observe, with the values we get from the IDM model. And it does this at every time step. So for each time step, we get a separate observation O, which, because it's a time series, depend on each other. So actually, we don't want to model this as a complete Bayes net, because we have all these interdependencies that would be very complicated. Instead, we consider just a conditional random field, and we model the probability for a given hypothesis as basically the moving average of the scores for the individual time steps weighted by the prior probability for this hypothesis. And it turns out that first, of course, this approach is much, much more faster because the constituent scores can be reused all over again. As it's a moving average, we only have to compute the newest, the score for the newest values of our acceleration. And also, it's more robust with noisy sensor data because if we have a false positive detection of a preceding vehicle on only one time step, then the influence of this time step is just influencing our overall probability by a factor of 1 over n. Comparing the two results, we see that they basically deliver similar results, and that even at very, very low false positive rates, we can still classify around or detect around 50% of our right turn maneuvers in the presence of a preceding vehicle, while obtaining a perfect score, you can't really see it, in the case of no preceding vehicle. Another interesting aspect of using an explicit model, as I said before, is that you can do predictions about the future. So in the simulation-based approach, we simulated the driver behavior for the time interval of 1 second ago up to the current point of time. So there's nothing to stop us just to simulate a driver behavior from our current point of time up to 2 seconds in the future, so as to see whether we can reach the pedestrian crossing within this 2 seconds. So this is very important if you want to design a driver assistance system, because the driver assistance system has to decide at some point to issue a warning. So it's not possible for this situation to use a constant velocity-based approach, because the driver is going to slow down before the intersection. To sum up, I introduced an IDM-based approach to driver intent inference, which is very simple and real-time capable. It takes into account the preceding vehicles, and it's able to express ignorance in situations where it's just not possible to say anything about the driver's intent based on the velocity profile alone, which is important if you want to combine this approach and let's say include other features like the indicator. Also, it allows us to predict the time to collision, which is important for the design of driver assistance system. Ongoing research focuses on the generalization to arbitrary intersections and multiple lanes, and how to generate the desired velocity profiles based on the path curvature. Also, we would like to have a probabilistic mapping of the preceding vehicle. You know, sometimes the preceding vehicle is somehow between the 2 lanes, so if you do a deterministic approach, then you might get the wrong results. Yep, that's it. I've come to the end of my presentation, and I'm looking forward to your questions. Thank you.
We have time just for one question. Anybody in the audience? Well, actually, I would have one question. I had 2, but you answered one in your future outlook, mentioning the path curvature. I can imagine that there could be some dependency. Have you looked also into dependencies related to the age and gender of the driver?
Actually, we didn't. As you could see at my slide, we only used 4 different drivers. So it's not really representative. On the other hand, previous works have shown that each driver is approaching an intersection at each time completely differently. Mm-hmm. So actually, it's a very, very high variance between the single or individual intersection approaches, even for one driver. So actually, this variance is much bigger than the difference between different drivers. So I don't really see that this is important in this context.
Okay, thank you very much. Thank you. Now I would like to welcome Mr. Karl Hammer from Autoliv, which is going to present the field of safe travel using location and motion information to increase driver acceptance of pedestrian alerts.
So I'm Jan-Erik Kallhammer. I come from Autoliv, and I want to also acknowledge my co-author, in this case lead author, Kip Smith. He's a professor at Naval Postgraduate School in Monterey, California. We have studied something we call field of safe travel, using location motion information to increase driver acceptance of pedestrian alerts. And the question really we are addressing here is that when should a pedestrian alert be issued? Should a system issue an alert for this pedestrian? Or this pedestrian? What if the pedestrian will be further away or further to the right? Would you still issue an alert? The there are different systems on the market. I just take here two examples here. Daimler introduced NV2 FOT in the E-Class in 2009, and BMW introduced what we refer to as Night Vision 2 with the 7 Series in October 2008. They have different characteristics, but the main thing here is that they both recognize and detect and warn for pedestrians. The functionality of the system is that you have a camera. There's no pointer here. You have a camera here up in the corner. In this case, it's a far infrared camera. Yeah, thank you. You have a camera. You run it to a computer, running some image processing. It's out to a display. Of course, here in the BMW, it's a display in the center console. The system is there to enhance the driver awareness of the situation and also warn the driver of pedestrians in the risk zone. And when such pedestrians are recognized, they are marked in various ways. Here I boxed them, but you can also highlight them by coloring in them, and you issue a warning. The question here is, what is the risk zone? And that's what we have studied here. There is an implemented pedestrian alerting strategy that I started from. We have, the alert is activated when a pedestrian is located in the static warnings region, the red zone, meaning that the pedestrian is straight in front of the vehicle's intended path. But you also issue a warning if a pedestrian moves into the vehicle path from the yellow zones here, or I guess the picture is, it looks more greenish there, but if they move from the side into so they would be in the vehicle's path when the vehicle is about to enter that area. The warning parameters are also adjusted by speed dependent. And I think that they all are perfectly logical. And I starting off here was more assumptions of how to define the width and the size of the red zones and the yellow zones, and how is the transition looking. That was my initial assumption. Of course, here in alerting strategies, the prerequisite here is that we assume perfect detection. That's of course an ideal situation that we are not quite there yet, but here we are assuming perfect detection. What do you do once you have detected the pedestrians accurately? And how do you then issue an alert in a wide variety of traffic contexts? Context may influence alerting criteria. The appropriateness of alerts may depend on the driving context. Drivers may rate favorable in alarming situations even when they were able to avoid the accident without an alert. And we suggest that alerting strategies must take into account this aspect, that the contextual factors that shape drivers' attitudes towards the situation in which the system issues alert. And the challenge then is to define adequate activation criteria. Here we have a pedestrian on the road, and the system decides to issue an alert in this case. If you fail to issue an alert when alert is justified, you have an immediate accident risk, and of course we want to avoid that. But if you issue an alert that's considered to be unjustified or unnecessary, even though it's a perfectly valid detection, you run the risk of if you have at least repeated such warnings, that the driver will fail to respond when he or she really needs to respond. And it's generally referred to as cry wolf, and you have a good reference there. So the issues and research questions we have here is that when should the pedestrian detection system issue an alert or a warning, and in the process to gain driver acceptance? And can we demonstrate the utility of a method that uses drivers' subjective acceptance as a criteria to guide the development? So basically we turn it around. So instead of trying to define an objective criteria that can be sometimes difficult to see, because actually most people will very rarely experience a situation where there will be immediate risk of hitting a pedestrian. So most of the experience we will have with the system is the situations that might develop into an accident. And then we suggest at least that it's maybe more appropriate to look at how do you gain acceptance for those situations. So you're basically using a subjective criteria to see if that can guide us in defining objective alerting criteria. So the methods we have used is to have a field operational test, data filtering, using a retrospective analysis to gain driver ratings, and then we done ANOVA analysis and regressions on those data. The field operational test was basically to throw it into a number of vehicles that we had available. They were retrofitted, and in this case it was a Volvo, and we had to put, and there were no such systems, so we had to put a special an add-on screen. We throw the PC and some other data acquisitions in the trunk, and then that's it, and we just started to record systems. Record on the field actual pedestrian encounters. We used company employees that had a company car, and in this first set we had roughly 2 months of normal driving. Some sequences, we took all the sequences we could get, but some had to be filtered out because of ambiguity. If you, for instance, have pedestrians at 2 different locations in the same event, if you then want to rate them, you don't really know which pedestrians or if there was a combined effect. So we excluded those. We also had some bicyclists in the sequence, and we didn't have enough data to do a separate analysis of them, and we assumed there would be different risk criteria for bicyclists compared to pedestrians. And we used all remaining clips. So they ended up with 57 clips, and we used 35 people to rate them. The retrospective analysis was, we had the volunteers to watch and rate each clip at a time, and they were randomized, of course, in order to avoid any sequence effects. And we asked a very simple question. We showed the clip, and then at the clip stopped, we showed the screen, and the question was, do you want to have an alert or not in this case? How do you accept it? And if you definitely do not want to react, you should take with the computer screen, the mouse, move it to react, that I do not want an alert in this case whatsoever. And if you definitely want one, you do the opposite. Most of the situations, however, were not so clear. It wouldn't have been a good experiment if all were accept and all were react. So most of them were somewhere in between. The method we developed is inspired by the hazard perception test used in the UK driving test, and then also the Van der Laan scale, but then simplified to be only one scale. And all of the participants rated all the sequences. Drivers and the lab subjects, we separated for those that had been driving, and also those with the system, and those that hadn't driven with the system, and seen if there was any difference. We converted the rate to rank in order to get any difference in the scale. I mean, the scaling isn't, they are not calibrated, so we used rank instead, the order of the here. And we found, and then we could use candles W on that things, and we found out that they were very consistent. I mean, 0.0001 is pretty good. And ranks with systems experience align with the ranks of volunteers without system experience, which is important because we can then have easier to recruit people for this rating. And these findings support that we can use the mean ranks in the continued analysis as a desired outcome. And we can also, for instance, here we see if you have the standard deviation on the y-axis, and here we have the average rank. So the case that was of these 57 sequences that was ranked the highest, and so forth. And of course not, but very expected is that events that were in between had more variability than ranks that were generally ranked very low, or cases that were generally ranked very high, which is another good confirmation of the data collected. Examples of ranked events. Of course, this is still images. Here we have a high rank. It's a pedestrian. There's a car coming here at about 90 kilometers per hour, and there's a pedestrian that's dashing over the road. And if the pedestrian would slow down, you would hit them. But the pedestrian doesn't slow down here, but it's difficult to know at the time when you issue the alert for the driver. And it was very consistent. Here is a medium rank one. There's a pedestrian coming to a zebra crossing. The projectors doesn't generally give very good credit to some of the images here in black and white. And there's a car in front. And if the car in front doesn't slow down, and if the pedestrian keeps his pace, we will pass before the pedestrian comes to here. But if the car in front slows down, or if the pedestrian speeds up, we would have to brake for him. And so it was kind of like indecisive. And it was also very consistent to be medium rank. Here you have a pedestrian that are in the middle of the road, which would be in the red zone I showed in the beginning. But people consistently saw that these pedestrian is actually, the road is curving and the pedestrian is actually on the other side of the road. On the original images, I mean, we didn't do it with this type of projector, so it was more clearly seen with the quality of the image where the pedestrian was. We then classified them, annotated them according to a number of criteria that we thought would be useful and has been discussed in the past. Locale, we rated them whether they were rural, suburban, or urban. Urban had to be continuous buildings. Suburban was not continuous buildings, but we used street lights as a criteria. And rural would be, of course, no street lights then. We also used the location of the pedestrian, whether they were in the street, whether they were on the left side of the road, whether they were on the right edge of the road, that means on the road but on the edge of the road, or on the right side, which meant on the sidewalk or beyond the sidewalk. We also categorized motion, whether they were in the same or the opposite direction of your own vehicle, whether they were moving into the street, or whether they were standing. And then we could conduct non-parametric ANOVAs on this, because it's in ordinal scales. And we found that pedestrian location, you can see here, that pedestrians in the street were ranked high, and also on the right edge, and they were highly significant. Pedestrians that were moving into the street were ranked high, but also pedestrians standing. And of course, pedestrians standing near the side of the road can anytime walk out into the street. So they were basically rated in the same way. There was actually a difference between whether the pedestrians were walking in the same direction or the opposite direction. And we think that there are other factors that we need to separate in this thing. But so we are doing another study with more participants, so we can separate them into more categories. We think it co-varies with something else. It doesn't co-vary with moving whether you are on the left or the right side of the road, because they were roughly balanced 50-50 there. And here's the data of the Krascovallis ANOVAs. Location, whether you were rural or urban, did not turn out to be significant, even though we thought was pretty certain that that would influence. We expected there is some other co-varying parameters as well here. And you can also see that we also had used the vehicle direction and road direction. We thought that whether you're on a straight road or on a curving road, or whether you're driving straight or whether you're about to turn would influence, because you have more of a sudden appearance of the pedestrian. But we had no significance on that. And those with an asterisk are those that are significant at 0.001, so it's a very nice significance. We could then generate the best fit linear model of this thing. So the rating has an intercept, and then a high value here before location, and the location was then set to 1, whether you were in the street or on the right edge, and then set to 0 if that wasn't the case. We use minimum velocity, so and then minimum x direction, meaning the distance in front of you. So the location was the most significant single predictor of alert acceptance. So if they were in the street or on the right edge. Minimum wide velocity may need some explanation. A strong positive value indicates that you're going from the left to the right. So if you were moving rapidly from the left to the right, you increased the rating. If you were moving rapidly from the right, from your near edge, this was done on right-hand driving, then you decreased the value. And of course, that means that if you're on the left side and you move rapidly, you're actually have speed enough to be in the way of the oncoming vehicle at the time it goes. But if you're on the near side, you actually have the time you will dash out of way before the vehicle has got there. Minimum X was also used, and that meant that the negative coefficient there means that the further away the pedestrian was, the lower the risk. But you see, it's not a very high weight. Otherwise, one would assume that this would, X distance would be, or the distance in front of the vehicle would be very important. And the 3 parameters explain about 61%, R squared is 0.61 of the variability. And that's a strong result when you explain human judgment. There are probably additional parameters that we have to look for that would increase the model's validity even more. So in review here, we have used driver ratings of the acceptance of alerts to identify the contextual factors that influence alert acceptance, and pedestrian location and motion does matter. We have used the ratings to derive a regression model that predicts how these contextual factors influence alert acceptance. Our method shows how you can leverage the scarce and expensive FOT data within the confines of the laboratory. So we could actually use then the data that are, each FOT data is unique, and we could then replicate them within subject study in the lab, which is very important then to reduce the cost of this type of exercises. And it provides consistent measures of acceptance in a controlled environment. It's a cost-effective tool that can help us bridge the gap between the field and lab-based experimentations. So lessons learned. What does it mean for our alerting criteria? Well, an alert should be given when the pedestrian is in the middle of the road or at the right edge. I said here the green zone. It was initially yellow, but turned out to be more greenish here. So in the green zone, moving rapidly from the left side into the street. So the size of the arrow is an indication also on the velocity of the pedestrian. Or on the right side and moving slowly into the street. And I think this all makes sense. Again, so the criteria we started off with was, in my opinion, very sound, logical, but when you see this one, well, this also makes sense. This is a way of refining it in a way that we didn't have any evidence that that's the way to define it before we had done this study. And then coming back to why did we call it field of safe travel? It's a classical article by Gibson from '38, where it talks about the field of safe travel, and here's one of the illustrations. And anytime we start to talk about autonomous driving, I think you should all review this article, because he was actually it's a theoretical one paper, but I think it's very interesting to see how we reasoned. Field of safe travel, the car driving in this way in the same direction is rather unlikely to move much in the lateral direction. So therefore the force fields here, or the force lines, or whatever you call it, are very narrow here. But the vehicle coming perpendicular into the road, whether he would stop or not is more uncertain, and therefore he encroaches more on your field of safe travel. the same time, a vehicle overtaking here, if he's going to dash in here, he will be less of a problem, but he may also continue overtaking. So it also means that we have intuitive results, and that also adds credibility to the method and the results. So in conclusion, field of safe travel should guide drivers' acceptance of alerts issued by, in this case, a far infrared night vision system, but it should probably is probably extended to all type of pedestrian detection systems. It hasn't been tested though for all types. And we suggest that field of safe travel should drive the design of alerting strategies. Additional studies with participants with less driving experience and from other demographic backgrounds are needed to verify that the regression results apply to a wider population of drivers. And the effects of mitigation systems, for instance, pre-impact braking, were not tested, but could be addressed with the method. And by that I close, and if you have any questions, glad to.
Yeah, please, we have a question there. We just go for one question.
Thank you very much, Jan-Erik, for this nice presentation. I was wondering, do you have any feeling of how these statistical approaches, this machine learning approach, if you say, compares to the approaches using generative models like we saw previously, like using measures of time to brake, time to react, whether there is some overlap in kind of results? And the second question is, I believe that you had a discrete set of states for on the road or off the road. How can you extend it to a more continuous state variable?
In this presentation, I had to limit myself, and there is a paper coming in human factors, and it's already online, but it will come in print edition, probably the next issue. We explain a bit more, and we are continuing this study. We have also looked into the continuous parameters, like we indicated that we use some of them here with the x and y, x distance and y velocity. So we have used that. And of course, you have then to take this thing as an input and then find what I call the objective criteria, so those that we can measure, that we can put in an algorithm. But this is a way of us to find what the algorithm should do, what is the desired outcome. I think that was question 2. Question 1 was...
comparison with the generative models.
Comparison where the annoying thing for me, I, for instance, use time to collision. And time to collision had not significant. It had some correlation, but definitely not significant correlation to what people like.
For the intelligent driver?
Well, becomes a more philosophical thing. I think it will take more time than we have here. But we all assume that various forms of time to collision is the norm here. And it may be, but the people that was rating this thing didn't correlate very well. It had a correlation, if I remember correctly, at 0.16, which is basically just over noise. So time to collision is not what people value in pedestrian alerts.
Okay, thank you.
Thank you, Mr. Karlhammer. I think that's it for now. Thank you. Okay, our next speaker is going to be Mr. Berthelot from Daimler, and he's going to explain us about a novel approach for the probabilistic computation of time to collision.
For the last speech today, I will present you a novel approach for the probabilistic computation of time to collision. So, as a quick reminder, I will present you time matrix, which are good criteria for criticality assessment, and the first time metric is time to collision, and there are also other time metrics as time to brake and time to steer, which represent the last moment for triggering collision avoidance maneuver. So if we consider non-probabilistic systems, we just use single-valued state for the objects, which leads to a Cripps value for the time matrix. Here, as example, TTC has just one values, and the reaction time matrix TTR are also one values. And this can lead to unrobust behavior, as shown in this video. So what's displayed here is an actual measurement. So on the top, you see a graph with the evolution of the time matrix, and the red, yellow rectangle is a measured object acquired with sensor fusion, and here you see the ego vehicle. And here a collision is detected, and the avoiding maneuver is also here displayed. And in that case, after a few seconds, the collision actually disappears and then comes back again. And if you consider the situation, if the yellow vehicle was on the left, the further left for a few centimeters, let's say 50 centimeters, then the collision wouldn't disappear, and the difference between the two situations are not so is not so big. So it's kind of an robust behavior. And another focus for this new method is also to account with the restricted computation resources in advanced systems. So in the design of this method, there was a big work on efficiency. So here again, let's take a look on the consequence of uncertainties on time matrix. On the left, you can see the Cripps values for single-valued states. And if you consider the uncertainty about the states, the time matrix are transformed into probability distribution. And these probability distribution are also scaled with the collision probability. So computing this collision probability is also an important step on determining the distribution probability for the time matrix. So this is why I will present you the method for computing the collision probability. I already presented this method last year, so I may make it quick because, but I present it again because it's really important to the next computation. So in order to compute the collision probability, we introduced a distance function in the time to collision computation algorithm with the following characteristics. So the distance function provides negative values if two vehicles are overlapping. That means if they have collided. And this function is also based on the maximum number because it's easily computed and it's also very adapted to rectangles. And as a consequence, this distance function are also an image space from -1 to +infinity. So if we take a look at the situation, on the left, I've depicted, on the right, I've depicted in situation, a crossing situation with two trajectories displayed, and on the graph on the left, you can see the distance evolution over the time between the two vehicles. In this case, there is no collision, so you can see the distance minimum here, symbolized with a small d, remains positive. But in case of a collision here, there is a collision, so the distance minimum is then negative. So by studying the probability distribution of this distance minimum, we can also compute the collision probability. Because the collision probability is also the probability that the distance minimum is negative. So first of all, we take an object with a state and also an uncertainty about this state, represented by the covariance matrix sigma. And we want to study the probability distribution of the minimum distance. So for that, we first make a Monte Carlo simulation, only to know how the distribution look like. So we slow thousands of samples, And for each sample, there is an initial distance here displayed on the left. And also for each sample, we perform a TTC computation, which also give us distance evolution curves. And for each curve, we can also get minimal distance. And from this Monte Carlo simulation, we isolated two types of distribution for the de-mean probabilities. The first type is just Gaussian distributed, here on the left. And the second type has a situation at -1 because the distance function cannot give values below -1. So for online assistance system, the Monte Carlo simulation is a bit of a no-go. So we used an approximation method, the Ascent transform. Some of you may know it from the Houston-Kalman filter. So we just compute a very few samples deterministically, depending on the state and the covariance matrix. And for each sample, we perform a TTC computation algorithm. And each sample leads to the mean, a distance minimum value, from which we can compute the mean and the variance. And using the model we isolated from the Monte Carlo simulation, we can approximate the distribution very well. And then by integrating from -1 to 0, we can also compute the collision probability. So now the question is how to approximate this curve here, which is the actual distribution of TTC, probability distribution of TTC. So if we consider the base rule, we can split this equation in two members. So on the right, the collision probability is already known, and we just have to find an estimate for the conditional probability. So we just have to find an estimate, yes. But the problem is, for example, each sigma points doesn't lead to a collision, so it's hard to compute this conditional probability just using TTC values. And the trick is to use a pseudo-time matrix, here defined as this underline overline TTC. And this pseudo-time matrix equals TTC if there is a collision and equals the time or minimal distance if there is no collision. Here the time of minimal distance is displayed on the graph, so it's the time when the minimal distance is reached. And as you can see, the quality of approximation is increases with the collision probability, because if we have a high collision probability, then the part of TTC values in the pseudo-time matrix is very high. And this is also a good approximation because in case of a low collision probability, the approximation error will also be minimized when we multiply this term with the collision probability. So here let's take a look at this flow diagram. So you remember it's a flow diagram for computing the collision probability. And here is the overhead for computing the whole distribution of time to collision. So we just have to extract the pseudo-time matrix values here from the computation of the TTC values. And again, performing Monte Carlo simulation, we could compute models for the pseudo-time matrix. And using the mean and variance, we can compute the corresponding parameters from this model and then compute the TTC distribution. And the important fact is this graph is that the most part of the computation is already done, because it occurs here by computing the TTC values, also the TTC algorithm, which is already done when we want to compute the collision probability. So, yes. And because we introduced a pseudo-time matrix, we don't have to perform any additional calls to the TTC computation algorithm. So now let's take a look at the results, as a comparison between the non-probabilistic system and the probabilistic system. So here, first of all, so on the left it's the same video as before, and on the right it's the new system. So here you can see the state taken from the sensor fusion algorithm, and the covariance matrix here depicted as both in position and velocity and acceleration is also actually already available from the Kalman filter, which is used in the fusion algorithm. We can also see the different trajectories, which are actually the trajectories computed from each sigma points. Here on the top of the video, you can see also the TTC distribution graphs. So in blue, this is a reference histogram computed with Monte Carlo, which is not real time, and on black will be the approximation, the real-time approximation of the distribution. So you can also see, even if on the left there is no collision detected yet, you can see that on the right there is already a collision probability of 6%, and it will be increasing. So here we come to the part of when the collision is detected on the left, and here we also have a collision probability of 98%, and so estimation and the real collision probability is of 95, so it's a real good approximation. And you can see that here the TTC was about 1.4 seconds, and actually it's already begins at 1 second and goes in up. So and then when we lose track of the collision, because the object is a little bit deviating, you see here that the collision probability is far from zero. It's always still 30%. So therefore, using this new method, you can increase reliability on your criticality assessment. Yeah. So here, when the collision comes again, you have, so here there is no way anymore to avoid the collision, and here you see it's linear in the time, and you have also fast 100% collision probability. So as a conclusion, I presented a novel and efficient algorithm for estimating the collision probability, also the probability distribution of TTC, excuse me. And therefore, I studied the influence of sensor uncertainties on time metrics. I designed distribution model regarding Monte Carlo simulation, and then I used an efficient approximation method to approximate this distribution. And yes, I forgot to mention, but this algorithm can also incorporate situation-specific sensor uncertainty because it takes the covariance matrix directly from the Kalman filter, and it's regularly updated. And so it's also real-time capable, so I have made some computation time comparison. So if you use Monte Carlo, the estimation of this histogram took about 1.5 seconds, and using the uncertainty transform, it took about 2 milliseconds if you have a covariance matrix of dimension 6. And if you just have an uncertainty on the position, it just takes 0.9 milliseconds. So for the future work, I will extend the presenting approach on situation with multiple objects. Here I have made a small example. So you have a situation, a crossing situation with 3 objects. So for each object, you can compute the TTC distribution with the method I just presented. But if you want to compute the overall distribution for the whole situation, you have to combine all the 3 distributions. And it's like finding out which, with which objects a bigger vehicle will collide, and that in a probabilistic way. So you have to regard correlation between vehicle and computation. It's not just the sum of the 3 distributions. It would be too easy. And also I will try to estimate the distribution probability of the other Russian metrics like time to break and time to steer. Thank you for your attention.
Thank you. We have time just for one question. Anybody in the audience? Yeah, please. Oh, she's coming. Yeah, yeah. Down the left.
Could you go one slice back? This MC, what is that?
Monte Carlo simulation.
Yeah, but let me see. We had a talk yesterday from a Daimler person about collision avoidance. You know, break down or make a decision between breaking down or you try evade
Yes.
the car, depending, of course, on different factors like the speed and so on, stuff.
Mm-hmm.
But this Monte Carlo thing that would be needed, and 1.5 seconds is a long time for such a decision.
Yeah, it's yes, that's my point. It's not used on the system, it just watches here to compute a reference and find out how the distribution looks like. And then, when I found that out, it's no longer needed. So, and the system, it just will be this 2 milliseconds approximation.
Is that already, it's still in the experimental phase, right? It's not yet part
No.
of the, it's not yet in commercial use. Okay.
No.
Thank you for the
It's
information.
research.
Thank you, Mr. Bertolone. So this paper was closing basically the active and passive safety session. I would like to invite the people to stay in the room as we are having actually the ceremony award that should take place. Okay. I guess the organization will actually take the lead on that.